Welcome back, folks. We're going to be talking about sinusoids a lot. I thought it might be worth it to just put one up on the screen and kind of look at the different values that are important around the sinusoid before we jump in and we start doing animations and flipping them around and stuff. So, you know, I thought better of the transition I made in the last video. I think we should do this first. Okay, so let's see. Here's a cosine. I started with a cosine. A lot of things we do in this class are cosines. We're going to do a little bit with sines, mostly with the sines. We're going to convert them to cosines. So you got to be right with all this stuff. If for a cosine, if we want to take the sine and move it over. But those are going to be all of our voltages and all of our currents for the rest of the class. Almost the rest of the class. Okay, so here's one. We call it a period of cosine. Okay, now this waveform has an amplitude, and that amplitude we mark as the letter A. Okay, and its positive peak up here is at positive A, and its negative peak down here is at negative A. Okay, and it's going to take whatever unit of the function, whatever unit you're trying to represent. So if you're representing a voltage, it's going to be in volts. If you're representing a current, it could be in amps or milliamps, anything along those lines. Just because we're using functions doesn't mean that we get to ignore units. Okay, and the amplitude is going to take on the unit of the function. Okay, sinusoidal waveforms, cosines included, are periodic. They're going to repeat. And we're interested in how long it takes this waveform to repeat. So how long, get this in a different color, just to break it up visually, how long does it take for a waveform to repeat? Okay, think of it as a period of time. And that's really what we're after, is the period of time. Let me move this stuff down a skosh. Okay, and since we're measuring a period of time, we are going to measure that in seconds. So the unit in this case is seconds. Okay, lowercase s for that one. You may see it written formally. You may see it written formally as, if I have the function v of t, okay, some voltage, then that function needs to be equal to itself if I jump forward in time by some constant value, and we call that constant value a period. So looking at our waveform over here, we can say, well, from here to here, that waveform is going to be the same. If I move down here and this waveform continues, right? If it were to continue down, I could say from here to here, it's going to be the same. And we think of that time period as the period of this waveform. So this distance we call capital T, the period, and we measure that in seconds. So that's the amount of time it takes for the waveform to repeat. We sometimes describe that same phenomena in a different way. It's actually the inverse, as frequency. How many times does it repeat in 1 second? So how many times does the waveform repeat? It's behind my head. In 1 second. You could even say, how frequently does it repeat in 1 second? Okay. Move that stuff down there. Okay, in order to find that, we take the period, okay, which is measured in seconds. And I want you to think of it, it is measured in seconds, but there's this unitless thing because it's how many seconds it takes to go for one cycle. So it's seconds per cycle. Okay, so let's talk about seconds per cycle. Okay, but cycle's really unitless, so a lot of times we just leave that off, and when we write it, we just say how many seconds it takes. Okay, so in order to get how many times the waveform repeats, we need cycles per second. And that's as simple as taking the period. Let's do this the other way. Okay, if we want to find the frequency, we just take the period and we invert it. Right, and if we're thinking about this alternate wave unit here, then the unit is going to be in cycles per second. So how many times does it repeat per second? Okay, it becomes a little cumbersome to say cycles per second over and over again, but I want that conceptually in your head for what's going on. We name this one. Okay, we name it after another old dead guy. This guy was named Hertz. Okay, so also known as AKA Hertz, and we abbreviate that one with a capital H and a lowercase z. So that's where you start getting megahertz, gigahertz, kilohertz, terahertz if you really want to go nutty, and that's part of the waveform. That's one way we can describe how quickly the waveform is repeating. Okay, let's grab this one. Let's grab this one. Let's grab these two that I had a moment ago, and let's bring them over here. Okay, because closely related to frequency is something called angular frequency. It's the same concept. It's how quickly the waveform is repeating, but the unit is a little different, and it makes things mathematically a little cleaner. We don't have the conversion between cycles and the angle radians in radians all over the place. So it gets rid of a lot of constants, and it's just overall a little cleaner when we start doing some of the derivations we need for this stuff. Okay, so this one is how many radians does the phasor, so this is going back to that phasor discussion. We're going to dig into that deeper too. Phasor, how many radians does the phasor rotate in a second? Okay, so the phasor's rotating, and when it rotates one cycle, how many radians has it rotated? So in one full revolution, how many radians are there? And we can get to that pretty easily. We use lowercase omega for this one. We can get to that pretty easily by saying omega equals 2 pi radians, because we have 2 pi radians in one cycle, right? So thinking back to these units all the time, and that is going to be multiplied by f cycles per second. Okay, so we get radians per second, and that's the unit of angular frequency. So if I'm going to write that more compactly, we're going to say omega is 2 pi f. It's just a different way to describe what's going on. So that's a good one to walk away with. So is that. Okay, since you're going to have to do these conversions. All right, we can do that the opposite way. We can say that the frequency is omega over 2 pi. Okay, just solving that for f. Go ahead and check the units yourself, because I know you're bored sitting at home just like I am, and you'll find that the units work out nicely for that one as well. So the units in that case, looking at the units here, are in radians per second. So a lot of times I'll write radians per second. Sometimes you'll see inverse seconds because radians is supposed to be unitless. But a lot of times we'll explicitly write rad per second just so that we're being as clear as we can in our communication. We never quite get there, but we always aspire to be as clear as possible when we're communicating these values. Okay, phase shift. The last bit of this. Phase shift is where the waveform starts. So this one I have starting at 0 degrees, and we'll look at why that's 0 degrees in the next videos. But this one's starting at 0 degrees. Phase shift is how far we're moving in time. So maybe this waveform, I'm going to try to draw it. You think I can do it? Hold on, let me use this as a guide. Okay, so we're going to come down here. I'm freehanding this. I hope you're impressed. Okay, and then up like that. And then this one's going to come down like that. Hey, look, that's a sine wave, isn't it? It's actually a shifted cosine right now, and we're interested in how far we've shifted from here to here. Okay, and that's going to be our phase shift, and it's measured in angles. We'll dig into that. I'm going to make you do some conversions. That's going to be 4 or 5 videos from now, maybe 3. And we'll dig into the details of that, but it describes how far the starting point of the cosine is shifted. And we're going to measure that either in radians or degrees. Okay, so how far is the waveform shifted? In time, but even though it's measured in time, we're going to quantify it using angles. Okay, so the unit on this one is either degrees or radians. All right, and think back to how you do those conversions. Hopefully that's somewhat fresh in your head. But if we want phase shift in degrees and we have it in radians, then we take the phase shift in radians and we multiply it by something. So we want to get rid of radians, so we're going to divide by pi, and we want it in degrees, and pi is equal to 180. Okay, so this is in pi radians. So radians and radians cancel, and we're left just with degrees. You can always flip that around, which we will have to do frequently, and we'll say if we want the phase shift in radians, we take the phase shift in degrees, and we do the opposite. We multiply by pi radians, and pi radians is equal to 180 degrees. Whoops, 180 degrees. So that degrees cancels that. Hold on. That degree cancels that degree, and we're left just with radians. So those are also useful. Hopefully review. They should be review, because you've dealt with radians in previous classes for sure. Okay, that's kind of the important values that we have around a sinusoidal waveform. And we're going to use all of these. You're going to have to be able to identify them from a time domain plot. You're going to have to be able to move them into the phasor representation. All of that stuff is coming up next, but hopefully this gives you some comfort with the words that we're going to use to describe the parts of a sinusoidal waveform. Okay, phasor animation's coming next. We're going to turn this into a complex number, and I think it's cool. My kind of cool. Stay tuned and good luck, folks.